Chapter 8, Potential Energy and Conservation of Energy. So, conservative forces. A force is conservative when the work it does on a moving object is independent of the path between the object's initial and final position. In other words, if you have your object starting from this point, point A, okay, and ending up in this point, point B, then the conservative force work does not depend on which path you're taking to go from point A to point B. Either you're going from this one, second one, or if you're going within a straight line. Okay, its work is independent of the path between the object's initial and final position. A force is conservative when it does no work on an object moving around a closed path. In other words, if you are starting from here, point A, and then going all the way and ending up in the same point, then the work is 0 in that case. Okay? And a force is conservative if the work it does is stored in the form of energy that can be released and used later. Okay, so these are the three most important definitions of conservative forces. So work is independent of the path. As I said, a force is conservative when the work it does on a moving object. It's also important that the object should be moving, by the way, because otherwise there is no work at all, is independent of the path between the object's initial and final position. For example, if I have a ball here at this point, it doesn't matter if it's dropped directly to get to this height or if it's going in a projectile type of motion to get to this point. It does depend only on an initial and final position. Okay, for example, the work done by gravity here, okay, is F dot D, right? F is mg. D is the change in the height. So it was initially in height h0, finally in height h final. So that's the displacement that I have. And then I have cosine of the angle between the force and displacement. In other words, I have cosine of 0 here, which is always 1. So that's why the work of gravity is mg h initial minus h final, or the change of height. This is change in the height, okay? So, in other words, if I want to show it here, this is h0 minus, or h initial minus h final. Okay, that's the displacement that we have right here. Okay, so work is 0 on a closed path. So if initial height and final height is the same, for example, a force like gravity, then the total work done is 0, because obviously if this quantity h0 minus h final, or h initial minus h final is 0, it means the object has come back to its initial position, just like a roller coaster here that you have. Starting from this point, going all the way to this path, and then coming back to the same point. Initial and final height is the same, and thus the work done by gravity is 0. Okay, so a conservative force will do no work on a closed path. Okay, so non-conservative forces examples. For example, as I said, there are two different types of forces: conservative forces and non-conservative forces. A conservative force like gravity, just like the examples that we talked about, and a non-conservative forces. Consider, for example, kinetic friction. Kinetic friction is this. Remember from before? So it always do a negative type of work. The work done by a friction is always negative, unless, like an example that we talked about it before, a box in the back of a pickup truck, then that would be positive. But usually, most of the time, 99% of the time, the work done by kinetic friction or by friction is negative. Okay. Even if the object returns to its original position, work has been done from friction. Okay. So it does depend on the path, because friction depends on the path, depends on the surface. Okay. So you're dealing with the work done by a force that does depend on the path. Okay. So work is done on a closed path, even if the object starting from this point A, going all the way and coming to the same point as end, the work is not zero, okay, for the non-conservative force. And it's the work depends on the path taken. So just like friction, it does depend on the path. If you're going on a longer path, you're doing more work for friction. So these are the examples of the non-conservative forces. For example, here, work done by friction on a closed path is not zero. So I have a box starting from this point, point A, right there, okay, and going all the way to point B, then point C, and then point D, and then coming back to point A again. So I have a work done by a force and a closed path, but it's a non-conservative force, okay? So from A to B, I have a box moving with a magnitude of D, all right? And what I have here is W of kinetic, because it's moving, okay, is force itself times displacement, dotted with displacement. Work is kinetic friction. D is just D, whatever the displacement is, and the cosine of the angle between the force and friction. This part is always -1 here, because friction is negative in the opposite direction of motion. So what I have here is negative f of k times displacement. And what the f of k is, so it is equals to negative f of k is mu k dot n, or mu k times n in this example, okay? And so mu k, let me actually write it a little bit better. Mu k times n times the cosine of the angle, which is -1, which I have it right there, times the displacement d. So I have negative mu k, n is always mg in a horizontal surface. So I have n, which is mg, and then I have d here. So the work done in this case by a frictional force is negative mu k mgd. So negative mu k mgd right there. And if I go from B to C, we'll do the same thing. If the displacement is the same, from C to D, the displacement is the same, so the work will by the friction will be the same. And from D to A, I'll do the same work. So technically, I am doing the same work 4 times. So the total frictional force, or work done by friction, would be 4 times, the mu k mgd, which is the work done from A to B or B to C. But you have to multiply by 4. It's not 0 then, so it is not 0, because it's a non-conservative force. If it were a conservative force like gravity, because you've come back to point A, you haven't moved vertically, your height has not changed, then your total work would be 0. But in this case, for a non-conservative force, a friction, it is not 0. It has a value associated with it. Okay. Conservative and non-conservative conservative forces. So a conservative force allows conversion between kinetic and potential energy. Okay, gravity and the spring forces are conservatives. So this is important to keep in mind. If I ask you, give me two examples of a conservative forces, you can say that the gravity and the spring force are conservatives. Okay, they allow conversion between kinetic and potential energy. The work done by between 2 points by any conservative forces, A, can be expressed in terms of potential energy function, is independent of the path between the 2 points, okay, and is zero if the starting point and the final point would be the same, or if we're going in a closed path. However, a force such as friction, okay, is not conservative. So friction is not conservative. So here I have friction, which is not conservative, and it's called a non-conservative force or a dissipative force. All right. So this is also important to remember. So let's take a look. So if you're looking at this table from the book, table 6.2, I have conservative forces here. Okay. And let me actually change the color to be consistent. Conservative forces here and non-conservative forces here, all right? So for conservative forces, gravitational force, elastic spring force, or electric force, these are all the conservative forces, okay? So their work does not depend on the path, it depends on the final initial position. On a closed path, they will do zero work, things like that, okay? But a non-conservative force, okay, static and kinetic friction, air resistance, which is some sort of a friction, by the way, tension of the rope, okay, normal force, and propulsion forces of the rocket. So these are the examples of non-conservative forces from the book. Now, let's talk about gravitational potential energy, or GPE, or just PE. Sometimes we use U to show it. I'm going to use U because I'm an old dude, so I just wanted to use U. It's an old notation of writing potential energy or gravitational potential energy, okay? As I said, the work of gravitational potential energy does not depend on the path. It does depend on final initial position. If you remember this basketball, so it does not matter if you're starting from this point going like this in a projectile type of motion, or you're just falling this down. Since the final and initial height are the same, you're doing the same type of work, okay? So gravitational potential energy, the work is mgh0 minus, or mgh initial minus mgh final, as we saw over there, okay? So the gravitational potential energy is energy that an object of mass m has by virtue of its position relative to the surface of the Earth. The position is measured by height, as we know, okay, h, of the object relative to an arbitrary zero level. So if I want to show potential energy, which I have at U equals mgy, or I can say U equals mgh. Okay, so that's the potential energy formula that I am going to use extensively. So gravitational potential energy, work done by this work, this force is, as I said, it is conservative, so it does not matter which path you're taking. If you start from this point with height of h0 initially and ending up in this point with height of h final, okay, so the displacement is, for example, s here, or d here is your displacement, okay. As long as you're going downhill, work from gravitational potential energy is positive. This is also another very important factor. So as long as you are going downhill, the work done by gravitational potential energy is positive, independent of the path, only depends on the change in height. So work done by gravity or gravitational potential energy is force, which is mg, times the displacement, which is change of height, or d here in our case, which is h0 minus h final. Okay, so this d is h0 minus h final. All right. And it is, if you're going down, it's always positive. It is always positive. And the reason for that is very obvious. Remember the sign. So for example, if I want to write the work formula, I would say F dot D or F dotted dot product with D. So I have F D cosine of theta. And this cosine of theta is important because mg is down, okay, towards the Earth center. Your displacement is also down, so they are in the same direction. In other words, this cosine is cosine of 0, which is always 1. So in other words, you're doing a positive work if you're going down. But if you were going up, then your mg is down, but your displacement is up. And then that cosine of theta is the cosine of 180 degrees, which is -1. So in other words, you're doing a negative work. Okay, so keep that in mind. If you are finding the gravitational potential energy, work, if the ball or the object is moving down, your work is positive. If it's going up, your work is negative. Right? So gravitational potential energy is work. Let's take a look at this. So I have a box here. All right. I have a box here. Starting from, let's see, starting from this point. All right. And having a change of height. So in other words, if I want to write it a little bit better, let me actually get this clear. All right. So this is our initial point. This is our final point. Okay, so I have work done by gravity being mg times displacement, right? So I have mg, the displacement is y2 minus y1, okay? But y2 is smaller than y1, okay? So this value of y2 minus y1, since y2 is smaller compared to ground, so this is y2, this is y1, all right? So y2 minus y1 is a negative number, all right? So I can say that I have mg delta y, just having the change of the y or h, but I will keep this negative right there. All right. So in other words, if I am writing it like this, I would have included everything that I am looking for sign-wise, positive or negative-wise, okay, in my formula. Let's take a look to see what I mean, because it might be a little bit confusing, but believe me, it's very easy. So if you're looking at this, if you are moving down, all right, if you are moving down, the box is moving down, or you have a problem that you have an object, it's moving down. So mg is always down, as I said, and the displacement is always also down. Okay, so this is the displacement. And the displacement is final height minus initial height. Okay, so final height minus initial height. In other words, this delta y here is negative. All right. So negative times this negative here will give you positive. And we know if you're going from top to bottom, if you're going from a higher position to a lower position, then your work done by gravity is positive. We know that. Let's test the other one. If mg is down, but you are going up, so that's your displacement d. All right, mg is down, displacement is up, delta y is positive, okay, because you are going from a lower or a smaller height to a higher height. Okay, so delta y or delta h is positive, but we know the work done by gravity is negative because the mg and displacement are in the opposite directions. Okay, so if you keep the formula like this, negative mg delta y, you will have included the negative sign in your calculations correctly. All right, so let's take a look what I meant by that. Remember this? As I said, if the mg is down and the displacement is up, the work is negative. We know it because they are in the opposite direction. And if they are both in one direction, mg is down, displacement is also down, then you're doing a positive work. Okay, so if you keep the formula like this, that I have it right here, let me actually highlight it. If you keep the formula like this, then what it means is that you have included this negative sign in your calculations correctly. Okay, so you don't be worried about if it's positive or negative. Whatever that this formula is giving you as its sign, then you keep it. So here, if you are going down, the delta y is negative. So you're multiplying a negative number with a negative number, and you're getting a positive outcome. But if you're going up, the delta y is negative. The delta y is positive here, and the positive is multiplying by negative will give you a negative. So here I have delta y being negative, but here I have delta y being positive. Here I have work done being positive, work done being negative. If I keep the formula like that, negative mg delta y, or or I can write it like this, negative mg delta h. Okay. So the work done by conservative force, or just like what I had before, delta U, or change of the potential energy of the object. U was what? mgh, correct? Delta U is U final minus U initial. Okay, U final is mgh final minus mgh initial. So if I factor out mg, I'll have mg h final minus h initial. Okay, and in other words, if you multiply it by a negative, okay, you'll get something like this. If the final height becomes 0 in our case, because it is at the level of ground, so the final height of final becomes 0, okay, then this guy is 0. So once it hits the ground, or water in our case, this is 0. And thus you're having a negative mghi, negative mghi, okay? So kind of looking like this. Or in our case, negative mgy, because it says initially it was at y right there. So this is the height initially, okay? So elastic potential energy, all right? So this is something that we're gonna cover in the second part of the video. If you have any questions, comment below. And let's go to the second part right after this.